All right. So you've probably talked about solubility in other classes, and we've referred to it briefly, and also we've had some conversations about solubility in this class in terms of ionic compounds. Some are soluble and some are not soluble. But we can also talk about solubility of organic compounds into different solvents. All right. So here's an example of two compounds, water, H2O, and CH4. All right. Water, I'll draw the molecule. It has the ability to have a dipole-dipole interaction. It also can do hydrogen bonding. CH4, on the other hand, no polar molecule, or no polar atom in there, no polar bonds, it's symmetric, all right? So this compound will not have any dipole-dipole, will not be able to hydrogen bond. In fact, pretty much all this can do is dispersion forces. Do you remember, Fred, what the names of the different kind or other name for the term dispersion forces is?
Was that Fred?
No. I was just making that up, remember?
I know. Let's see. London forces?
That's right. Dispersion forces are called London forces, all right? They're also called induced dipole or instantaneous dipole or van der Waals interactions, all right? So anytime you see any of those types of interactions, they're referring to this dispersion forces, all right? So what we would see, and this is the case, is that this methane does not dissolve into water, all right? The two are not soluble because they have different types of intermolecular forces, all right? On the other hand, this compound here, CH3 with an oxygen and then a hydrogen, right? This is methanol. What intermolecular interactions can methanol have with its neighbors?
Oh, is that an oxygen on a hydrogen?
That is. So what does that tell you?
It's going to have a dipole. It's going to be able to hydrogen bond, right?
That's right. It can hydrogen bond. So because methanol here can hydrogen bond, H bond, which is a dipole-dipole, right? Dipole-dipole, hydrogen bond, dipole-dipole, and this can hydrogen bond, dipole-dipole. Water and methanol are going to be miscible, soluble together, okay? Miscible means when you mix two things together and they dissolve together. They don't create a heterogeneous mixture, but they create a homogeneous mixture. That miscible is a word that we use. So the phrase like dissolves like means that compounds that have the same types of intermolecular forces that they can offer to their neighbor will dissolve each other. All right? That being said, methane then can dissolve in something like octane. 1, 2, 3, 4, 5, 6, 7, 8. Octane is C8H. I'm not going to draw the hydrogen, C8H18, but it's a liquid at room temperature, and methane can easily dissolve into it because the only types of intermolecular forces that it has are dispersion forces. Okay? Surfactants are things like soap. All right? Soap, I don't know if you have ever seen the chemical structure of soap, but it has a long carbon chain which is very hydrophobic. It only has, hydrophobic means water doesn't interact with it because water has dipole-dipole and hydrogen bonding, but this can only do dispersion forces. Soap also has, though, however, a head which has strong oxygen, or strong electronegative atom like oxygen at the end here. And so this little portion of the molecule can be dissolved in water, or water can grab on to that little portion. And so when you put something like soap into water, we'll show you a little bit later, but what happens is, if I were to draw this chain a little bit smaller and say, okay, here's the chain and there's the head, the chains will all line up and repel when you put soap into water. This is what happened. And that's why you get these bubbles that form in water, right? All of the water-soluble ends, they go to the outside, and on the inside, you get your hydrophobic regions, or your dispersion forces portion, all clustered in the middle. And we have a name for this. This is called a micelle. Micelles. So soap forms these micelles, and soap is helpful at removing hydrophobic material like bacteria or oil from your hands, because the hydrophobic region here, the part that has London dispersion forces, right, can interact with the oily portion, or the outside of bacteria, which is often hydrophobic as well. And the head can be pulled off, or can be used to pull the soap and whatever's attached to it, grease or bacteria, off of whatever surface you're trying to wash. So those are surfactants. Which of the following is not a true statement? Only nonpolar molecules exert London forces. The greater the mass...
A.
What?
A is the answer. I remember that everything has London forces.
Okay, very good. That's right. It can be polar, nonpolar, whatever. There's always going to be London forces. The greater the mass, the greater the London force. Is that true?
It must be true, but let me think about it. Yeah, that's what you were showing, right? The greater the mass, the higher the boiling, melting point.
That's right. Another name for London force is induced dipole attraction.
Yeah, you just said that.
Okay, very good. Let's see which kinds of intermolecular forces will exist in these compounds. All right? What do you think here? What kind of intermolecular forces?
Well, it looks like a dipole, but not hydrogen bonding.
That's right. Dipole, but not hydrogen bonding. How about this one here?
Let's see, you got oxygen and hydrogen, so definitely dipole. Yeah, it's going to hydrogen bond with itself.
That's right. How about this one?
Bromine, carbon. Let's see, is that a hydrogen bond?
Not a hydrogen bond.
Oh, I mean, is that a polar bond?
Well, it's not very polar if it is, but even if it is very polar, what do you have here?
Oh, I guess it's symmetric, so that's just going to be van der Waals interactions, or what do you call them? Dispersion, London forces, that sort of thing, right?
Right, good. What about neon?
You don't get anything with just an element, do you?
Well, there's always something, right?
Oh, yeah. Does London dispersion forces?
That's right. Very good. London forces. Okay, very good. Now, I'd like to bring your attention to something on the periodic table while we're here and talk about this a little bit. This is something that's very important to remember. It helps you kind of remember your London dispersion forces. Okay? What it is that fluorine, FF, that molecule, is a gas at room temperature. Chlorine is also a gas at room temperature. Bromine is a liquid at room temperature. And iodine is a solid at room temperature. So, when you see something that changes from a gas to a liquid to a solid, I mean, it's not the same compound, but you see it's just chlorine, bromine, and iodine. What is it that's causing iodine to be a solid at room temperature and chlorine can be a gas at room temperature?
It's intermolecular forces, right?
That's right. It is intermolecular forces. Now, what kind of intermolecular force? Is it a dipole-dipole? Or is it a London force? It's not a hydrogen bond. There's no hydrogen.
Yeah, no hydrogen. Well, what does chlorine look like?
Well, it pretty much looks just like I drew it there, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
So no dipole, right?
That's right. None of these have dipole moments on them. All right?
So is it just London forces?
That's right. It's just London forces. As iodine gets larger, then it sticks to its neighboring iodine molecule easier. So chlorine is a gas, bromine is a liquid, and iodine is a solid. So again, that's a nice little thing to remember to remind us how strong London forces or induced dipole interactions can actually be. Okay. Arrange the following in terms of increasing intermolecular forces: CH4, CO2, and HF. What do you think?
HF can hydrogen bond, so that should be the greatest. So I'm thinking C. Let's make sure it's not D.
So HF has the strongest intermolecular forces. How did you know that?
Well, you said that hydrogen bonding was pretty strong, right?
That's right. HF can do a dipole-dipole interaction with hydrogen, so therefore it's a hydrogen bonding. What can CH4 do again?
It was just, what you call it? London forces.
That's right, London forces, dispersion forces. So what can CO2 do?
Let's see, CO2. You can draw it there. I remember it, though. It's just linear, and so it also has just dispersion forces.
That's right, just dispersion forces. Now, who's going to have greater dispersion forces? CH4 or CO2?
How would you tell?
Well, just like iodine had greater dispersion forces than bromine, which had greater dispersion forces than chlorine, what you need to do is you need to look at the resulting mass of the compound. CH4 is pretty light, just 12, 13, 14, 15, 16 grams to make 1 mole of it. Whereas this one here, these oxygens are relatively large, 16, 16, right? And then 17, 18, 19, 16, 16, 32 plus 12, that's 44. So because this is 44 grams per mole, and this is 16 grams per mole, right? And they're both just London forces, you know that carbon dioxide is going to have stronger intermolecular forces compared to methane, CH4. So I think these are out of order, right? These are out of order. It should be HF and then CO2 and then CH4.
Now, how did you know that again?
It was simply the mass. So when two sets of compounds are being compared, right, we're looking at the intermolecular forces between one CH4 and another compared to intermolecular forces between one CO2 and another CO2, right? CO2 is much heavier in mass, and so that's the one that's going to have the stronger intermolecular forces.
Okay.
All right, good work. Good place to stop.